While we introduced the concept of non-uniform or accelerating motion in the last video with respect to velocity and velocity versus time graphs, now it's time to see how exactly non-uniform motion looks with position or x versus t graphs. So let's briefly remind ourselves of what exactly going from a velocity versus time graph to a position versus time graph with respect to uniform motion looks like. So this particular situation, I have a velocity versus time graph that starts at 2 meters per second. That's the initial velocity. And it goes at that for 2 seconds, stays at rest for 2 seconds, and then moves at negative 2 meters per second for 2 seconds. And if I want to move to a position versus time graph, the easiest way to do that is to go here and solve for these areas, because these areas will tell us the respective displacements at different points in time. Use a different color. So for instance, this displacement here would be 2 times 2, or 4 meters. No displacement here, so nothing there. And this one would be negative 2 times 2, or minus 4 meters. So now, let's translate that into the position versus time graph. And let's go ahead and suppose that this has an initial position of 0. We would have to be told that explicitly, but let's just say that's the case. So first off, we start at 0. And we're going to move with a displacement of 4 meters in 2 seconds. Then it does not move for 2 seconds. And then we will have a displacement of minus 4 meters in 2 seconds. That ultimately will bring us back to the same position. But what if we have a velocity versus time graph with a slope? And remember, if it has a slope, that means we have an acceleration, because the acceleration is the slope of that graph. It is the change in the velocity with respect to time. Well, we still move between this and a position versus time graph in the exact same way. We can look at these areas again. Let's try this one time real fast. Let's go ahead and look at this first segment here from this time to this time, and we have some little area. And I could say, let's imagine that our position versus time graph that we were told that we started at 0. And so in this first segment of time, we're going to move some distance. All right, we don't know exactly how much that is. We're going to move some distance. All right, in the next segment, well, if we were moving at a constant velocity, this area should be the same thing as that area, because each area is a certain amount of displacement per unit time. But now we're accelerating. In fact, if I look here, this is almost about, what, 1 time the velocity, or 1 time the area, 2 times the area, 3. So this whole segment here is almost about 3 times the area. So we have 3 times the displacement here from this initial position. So I have this initial point. Then I have to go up about, what, 1, 2, 3 times as much to get something that looks like this. And then in this next segment, I'm going to do this again. And this is going to be even further, an even greater area. So now I'm going to be moving not only to this point, not only to the same height straight up, but even further, causing it to do something like that. And what we see happening here is we start to get a curved graph and the position versus time graph. That curve indicates that acceleration is most definitely happening. And once again, these two graphs are visualizations of the same motion, representations of the same motion, but now we are looking specifically at non-uniform, otherwise known as accelerating motion. So we've already been familiar with position versus time and velocity versus time graphs, but now we're even going to start introducing acceleration versus time graphs, because when we have an acceleration, we can look at all 3 of these situations. So each of these graphs are actually tied together. First off, I have this one over here showing me that there is some sort of constant positive acceleration. This acceleration never changes. Well, if that is constantly positive, that means our slope on our v versus t graph will be constantly positive. And additionally, remember, if we know that, let's imagine that our initial velocity was 0 and our initial position was 0, that's at least a possibility, that this area is steadily increasing, which means that this is going to be steadily increasing at a higher and higher rate, and this slopes on this graph will be getting higher and higher and higher too. And we're going to go over that in more detail. But the real big thing we want to make sure we know, though, is luckily for us, we are only going to be dealing with constant acceleration situations in AP Physics 1. Meaning that we will only see segments with constant acceleration. We won't see anything beyond that. And what that allows is that means we should never have a slope on an acceleration versus time graph, because it'll always be constant segments, uniform accelerations. And that also means for a velocity versus time graph, we should never have curves. We will just have straight line segments. However, if we have acceleration on an x versus t graph, that definitely indicates there will be a curve. So I mentioned this just a second ago, but let's look at this curved graph in a little more detail, because remember, the slope of an x versus t graph gives us the velocity. But we no longer have a constant slope here because it's accelerating. The velocity is not constant. So therefore, we now have this curved x versus t plot, but then, well, if the slope's the velocity and it's not constant, well then how can I find the velocity here? This is where we start getting to that idea of instantaneous velocity. Because if I look here, the velocity at every instant is going to be different because the slope here at every instant is going to be different. Let's start down here near the bottom of the graph. And if I want to find the slope somewhere in this area, I am going to draw what is known as the tangent line to this graph. Now let's make sure we know what that means. So this is a tangent line, which means it only intersects the graph or the x versus t plot in one location. It literally just comes by and nicks the edge of the graph and then keeps on going. So here I would have some slope, and it would be relatively shallow, which means that our velocity at this point, not very high. If I then change, let's use this different color, and let's look somewhere over here. And if I draw a new tangent line, so it just nicks it right here. If I look at that, my slope has increased for this point here. And if I want to find the velocity over in this area, well, then I have to find, once again, a new tangent line. Oh, there we go, all the way up here. There we go. And once again, my slope has increased. So because the slope is increasing, when I say the slope, I mean the slope of these tangent lines that intersect the graphs at these very, very tiny intervals, that since the slope is going up, that means the velocity must also be going up. The same rules still apply. The slope of an x versus t graph still gives me the velocity. That still applies even when it's accelerating. So whenever we see a curved x versus t graph, there's really 4 distinct curves we might see. And you might think, well, aren't there other curves? And you're correct, but they're going to be combinations of these 4 shapes. I would highly recommend copying down these 4 shapes in your notes, and we're going to go through them one at a time. All right, so first off, let's look at a couple things here. We want to know, is the velocity for each of these curves positive or negative? Is the acceleration positive or negative? And is the object speeding up or slowing down? Well, 2 of these are a little easier to see, specifically the velocity and the speeding up and slowing down. And let's talk about why that is. First off, remember, the velocity we get simply from the slopes of these graphs. So therefore, if the slopes are positive, well then that means the velocity is positive. If the slopes are negative, that means the velocities are negative. So let's go through just this first one here. So let's say I have some slope here, so I'm going to pick a point and draw a tangent line. So the slope at this point is definitely a positive line, so that tells me that the velocity of this graph is positive, that the slopes are constantly positive, so is the velocity. Well, is there another one that is also positive? Well, actually, it is going to be this one down here, because if I look once again at a tangent line at, for instance, about that point, this is also a positive line. So this is also a positive velocity. Well, let's look at this one. That tangent line is negative. This tangent line is negative. Therefore, these are both negative velocity situations. Okay, so I can see that the positive or negative velocity I just get from are the slopes of the tangent lines, positive or negative. Now let's look at the next one that's a little easier to think about, which is speeding up or slowing down. Well, let's think about this in terms of the slope again. If we are speeding up, that means velocity is going up, which means that the slope should also be going up. We should have the slope be increasing in value. It should be approaching an infinite slope. So if I look in this first situation, initially I have a pretty shallow tangent line, but as I get further to the right, those tangent lines get steeper and steeper and steeper. So this is definitely speeding up. Is there another one that's speeding up? Well, surprisingly, it's this one over here. Because initially I have a fairly shallow, whoop, that was horrible, a fairly shallow tangent line, but then as I keep going further and further, the tangent lines get steeper and steeper. So once again, this is speeding up. Specifically though, now we are speeding up in the negative direction, whereas on this one we are speeding up in the positive direction. So additionally, if we instead slow down, our velocity is going to go down and our slope is going to go down. So let's make sure we have that working here. Now if I have this situation, I initially have a pretty steep slope, but over time the slope gets more shallow, which means we are in fact slowing down. Same thing on this one. Initially I have a really steep slope, but it gets more and more shallow. It approaches zero, so I am slowing down. Now we come down to what is possibly the trickiest one, the acceleration. Now if you remember, we talked about in the last video that there was a way that you could kind of reason this out. For instance, if I have velocity as positive, and I'm going to treat speed up as positive as slow down as negative. So I have a positive velocity, positive speed up, a positive times a positive gives me a positive. So this would be a positive acceleration. If I look here, I have, once again, positive, negative. Let me do that, all of them real fast. I have a negative velocity, and I am speeding up. Well, if it's negative times a positive, that tells me, okay, that's negative acceleration. All right, now let's look over here. Positive times a negative, so that would be negative acceleration, and a negative times a negative, that would be positive acceleration. Okay, well that's all well and good, but you might honestly be thinking now, I am never going to remember that on a test if I'm in a hurry. You know, how do you have to write out that whole chart, and things are positive and negative, and it hurts my brain, and how am I ever going to recognize this? I'm going to let you know that we have a nice, easy thing to do here. I'm done. So let's talk about this. This one makes a smiley face. Smiles are positive. Positive acceleration. This one also makes a smiley face. Positive acceleration. So smiley means positive acceleration. This one here makes a frowny face. Negative acceleration. This one also makes a frowny face. Negative acceleration. Now I'm going to pray to you that you do not write smiley and frowny face on your AP test or even on my tests. However, this is a quick, easy way to immediately recognize is the situation I'm looking at positive acceleration or negative acceleration, and it will not lead you wrong. Now, one thing I do want to say about it, if you are someone who's already in calculus, particularly I think if you're in BC, this is specifically telling us the concavity, which you find from the second derivative. That the acceleration is positive if you have a positive concavity. It is negative if you have a negative concavity. If you're non-calculus, Don't worry about that. Just focus on smiley face, frowny face. So let's look at a couple further tricks real fast. So just as a quick note, we just talked about the fact that if I draw something like this, and I want to analyze the situation, well, the slope is positive, so that would be a positive velocity. Specifically, this also shows me that it's a smiley face, so that would be a positive acceleration, and the slope is getting steeper, so that would be speeding up, right? We just talked about this. But this is not the only situation I can have all these factors. What happens if I start down here and do basically the exact same shape? Well, the slopes are still positive velocity. Still smiley face, so still positive acceleration, and the slopes are still getting steeper, so it's still speeding up. So even though these two graphs have two different initial positions, that doesn't matter. We still get the same sort of analysis. So don't focus on where is the graph starting, particularly on the position versus time graphs, because all of the graph shapes can be shifted around. Because remember, we can't get the initial position from an velocity versus time or an acceleration versus time graph for that matter. We have to be given that information separately. So it's okay if we have multiple possibilities here. So let's see one more trick. Because remember, one thing I mentioned was that those were the four types of curves, but we can combine them. So for instance, let's say you get some really crazy looking position versus time graph that looks something like that. And you might be thinking, oh my gosh, there's so much going on here. Just take it piece by piece. So if I look at this first section, I am getting more steep. My slopes are negative, so this would be negative velocity. I am speeding up. And additionally, it's a frowny face, so that would be negative acceleration. And this part here, there's a little segment where you might go, this really isn't frowny or smiley, so that tells me there's really no acceleration there. But when I look at these bottom segments, this is a big smiley face, so that's definitely positive acceleration. This slope on this side is negative, but then it becomes positive, so I have negative velocity over here, positive velocity, and I am getting more and more shallow, so I'm slowing down over here, and I'm speeding up over here. There we go. Just as a reminder, both of these were positive acceleration. And then this last portion, I have frowny, so negative acceleration, positive slope, positive velocity, and it is becoming a little more shallow, so it is slowing down. So just take it one piece at a time. Do not try to analyze the whole thing at once. Lastly, we want to get to the point where if we know one of these graphs, we can at least come up with possibilities for the other, so we can try and know whether or not our data looks good or not. So for instance, let's pretend I have some position versus time graph. Let's do some random shape. Let's say something like that. Alright, now if I was going to graph my velocity versus time graph here, I would look at this and go, well, initially it's a pretty big positive velocity, but it is approaching zero and basically ends at zero. So we're going to get something that looks like that. And if I look at this graph, that is a negative slope. Additionally, if I look at this, that is a frowny face. So I should have some sort of, I guess I should change my color, some sort of negative constant acceleration. There you go. Those would be one possibilities for the graphs. Now notice I don't have any exact numbers here, so we're really focusing more on the shapes and what they look like rather than specific numbers. So what are our takeaways here for non-uniform position versus time graphs? And this is ultimately the end of our first unit on kinematics and graphical analysis. Well, we want to know, can we explain how to find the instantaneous velocity from an x versus t graph? Remember, you find it from that tangent line, the tangent line being the line that only intersects the graph at one point. We want to be able to determine the following from any curved x versus t graph. Do we know if the velocity is positive or negative? Do we know if the acceleration is positive or negative? And do we know if the object is speeding up or slowing down? Remember, we really want to focus more on the shape a lot of times than specific numbers. And lastly, we want to be able to draw x versus t, v versus t, and a versus t graphs that match each other. I am not expecting you to be an expert on that yet. That's really going to be what we focus on for the next couple of classes. But I want you to become familiar with the idea that all three of those graphs represent the same motion, and we want to be able to identify what those should look like for any typical situation.